Okay, so we were, as usual, looking into negative feedback system with still in the block diagrammatic phase. And when we ended the last class, we said that we will try to figure out what will be the steady state error for a DC input or step input if I don't have an ideal integrator and I have a non-ideal integrator, right? And the input is applied at the location that is shown. So I asked you to work it out. So tell me what the output will be in terms of time. So let's write the ideal integrator out case first. So if P is 0, that is pole is at DC, infinite DC gain. So what is V naught? P is 0 and Vi is step input, let's say, and Vi equal to UT. So what is V naught?
By P dash, where P dash is.
Pardon?
The output voltage for the step input, right?
Right, with ideal integrator.
So with the ideal integrator, it will be omega u by k into 1 minus e to the power minus t by tau into ut, where tau is basically k by omega.
Okay, firstly, is this correct? Because firstly, omega u by k, what is the unit of that?
0. I think so, it will be 1.
Yeah, right. Yeah, it has to be 1 because at least for DC input we know, right? At DC, this integrator block gives you infinite gain, which means virtual round is 0, and you should get whatever. Okay, firstly it will not be 1; it will be k, right? So you are supposed to get whatever is the ideal scenario. Okay, fine, good. So what is now for generic P?
So generic P will be omega u by P dash, where P dash is basically P plus omega u by k.
What about the first stuff?
Omega u by P dash.
Omega u by k, P dash. What is P dash?
Omega u by P dash.
What is P dash?
P dash is basically P plus omega u by k. Then 1 minus e to the power minus P dash t.
Okay. Okay, so what about the rest of you? Do you think? In the numerator, omega u by k. But then it will not be, if you set P to 0, then it will not be k times, right? These are quick sanity checks. If you set P to 0, it should be the case. At least the steady state output should be equal to k. Steady state is when t tends to infinity, so the exponential goes to 0. So V0t should be k if p should be 0, right? How many of you did it actually? Can validate it. Do you think this is right or wrong? If you don't, if you haven't done it, do it. Okay, so this sanity checks of this expression checks out because if you set P equal to 0, you essentially get whatever you were supposed to get for an ideal integrator case, and I'm sure you are more familiar with the case where if I express it in this form. So what is the loop gain in this case? L of S? So if I take P out, this becomes by P, and this factor is essentially what we call as DC gain, because if you set P to be equal to, if you set S to be equal to 0, right, at DC, that is S equal to 0, the loop gain is omega U by K times P. Okay, so this is normally expressed, traditionally expressed in this form. Okay, where this DC gain, it becomes equal to omega U over K times P, right? So, now if you set S to be equal to 0, and this block essentially becomes A naught, right? And you can subsume the negative feedback network into this loop gain expression, simply because this L of S now contains that divided by K factor. And if you don't want to do that, you can express the integrator as some DC gain by 1 plus P and then go around the loop. You'll essentially get the same expression. But the key point that I want to drive home here is that you will get so this, when you look at this expression, you see that clearly when everything settles at T equal to infinity, or when at DC, right, at omega equal to 0, what do you get? You are supposed to get K, but you are not getting K. Okay, so there is an error. And so if I express this final DC voltage, what I am getting, so V naught T, this is real for, pardon? Where did you get? No, you mean in L of S or in V naught T? So you got omega U by K here. But again, if you set P to 0, your V naught P at T equal to infinity becomes 1, right? So if you set P to 0, it should be an ideal integrator case where it should be K. So something is wrong in that expression. Right? So I didn't purposefully go through the math, because math is quite trivial. You just, as long as you are not making algebraic mistakes, it's basically you do in Laplace domain, partial fraction, invert. Process is the same. What I'm trying to impress upon you is the fact that, how do you check whether your final output is right or wrong, right? You always do a sanity check, right? When you first learn to do division way back in class 3 or 4, how did you check? You went ahead and did a multiplication and checked whether your answer is right or not, right? So this is similar to that, right? So, you cannot just, be satisfied with whatever algebra you are, or whatever final answer you are getting out of your algebra. Yeah, you might have very high success rate in doing it the first time, but even then there's a need for revising what you are getting, right? So instead of going through the steps, you can also do another back of the hand calculation to check under extreme conditions whether your answer checks out, like T equal to infinity, setting some variable to 0, because you know what is supposed to be under ideal case. Okay, so so getting back to the steady state thing, so this you are getting to be omega U by P by omega U by K. I take K out because that is what it was supposed to be in the first place. So what do you get? This becomes now, if I want to always express, omega U is, I want to always club K and omega U together, because you see in the loop gain, they also club together. So it helps in getting an intuition of what is actually happening. So this is whatever you are supposed to get ideally, but you are not getting with the ideal situation because you have an additional term. And this additional term is essentially what? This is nothing but k times 1 by 1 plus 1 by DC gain of the loop. Okay, so what is this? If we now know this, I mean, this is what it is supposed to be. This also makes sense because ideally you would want the DC gain of the loop to be infinite. So in an ideal, when p equal to 0, in case of an ideal integrator, a naught is actually equal to infinity. So your steady state value is equal to k. But in this case, you have a steady state error. And what is the steady state error? Steady state error, we define it as the case, the value that you would have gotten ideally minus the value that you are getting in an actual case, right? So in this case, just error okay. So now, I mean, in the literature, you will see steady state error is often expressed as a percentage, not an absolute value. That also makes sense because for a given a naught, you might get a larger steady state error if k is larger, right? If you desire that, if your steady state error is a function of the gain, then it really doesn't make sense. Then it looks like you are getting higher error if k is large. So essentially, we try to express steady state error as a percentage of whatever the actual output is supposed to be. So as a percentage, so we express in percentage form as error by actual output, or rather, sorry, ideal output. Which means this is 1 by a naught, 1 plus 1 by a naught. Now, if a naught is really large, which anyway you would want to make, right? You might not be able to make a naught to be infinity, but you definitely would want to make a naught to be much greater than 1, which essentially means that this boils down to 1 by a naught. Okay. So this 1 over a naught is essentially the loop gain, right? The a naught is a loop gain at DC. And as you see that your DC loop, your steady state error will be, I mean, this is in terms of percent, right? So you'll have to multiply with 100. So your steady state error essentially goes down by the factor of the loop gain. So this is another way of reasoning that if you want your output to settle within, sometimes you will hear in some jargon that I want my output to be 1% accurate, or 1 ppm accurate, right? So what is essentially the spec is telling you is that whatever you expect, the output should not vary between, if you say 1 ppm means 1 millionth of the expected value, which means naturally from there you can figure out what a naught is supposed to be. A naught is supposed to be 1 million. So you have to design your integrator. It will be a non-ideal integrator because you will not get an ideal integrator. This is our model. So when the non-idealities of the integrator should not degrade your integrator loop gain by more than 1 million. Okay, that's what it means. So that's where these top level specifications help you to narrow down into what you are supposed to design. Okay, so when you are going and designing, when you are approaching somebody to design, and somebody is giving you an op-amp design, in reality, they will not tell you that yes, choose this gain, choose this bandwidth, and so on. So they will tell you what is the top level specifications that I require. From there, you have to narrow down. You have to narrow down and figure out what does that specification essentially mean. Okay. So this is one example of which I tell you that my output should be accurate within, let's say, 1 ppm. So which means that your gain should be, DC gain should be equal to 1 million. Okay. Okay. So, so this also checks out if you plot the loop gain. So now let's go back and plot the loop gain. So ideal loop gain was this. So this is L ideal, which was omega u by Ks. And in case of real, so by the way, I also asked you to check whether the pole here will exactly coincide. If you haven't, do it. If this is true, then obviously the point where you cut the 0 dB line will not change, right? The 0 dB line will, where you are cutting the 0 dB line, it will still be omega u over K. Okay. And this is. And this will be A naught, where A naught is the DC gain that we just saw. Okay. And now when you are talking about settling at DC, which means we are operating somewhere close to DC, or maybe somewhere very close to DC or at DC. Now, from the perspective of figuring out what the steady state output is supposed to be, the loop, this A beta negative feedback structure also helps us in that regard. Right. So in this case, clearly your V naught by Vi is 1 over beta, 1 by A beta times 1 plus A beta. So when the loop gain in this case is A beta, when A beta goes to infinity, you are supposed to get 1 over beta, but when A beta is real, it's not infinity, then you get a steady state error. You get an error, and the error is essentially inversely proportional to 1 by 1 plus A beta, that is 1 by loop gain. And in case of, so if you plot the loop gain, and I am telling you that the input is DC, which means you should be able to read off the loop gain value at whatever frequency you are interested in, and from that you can figure out what the steady state error is supposed to be. If it's supposed to be DC, then you look at the loop gain value at DC. If it's not supposed to be DC, then you look at the loop gain value at that particular frequency. Okay, so if you go by this logic that steady state error is inversely proportional to 1 by L mod of L. Okay, and I tell you that. And I ask you to find out what is, and I tell you that now I don't have DC input. I have a sinusoidal input. Okay. And I tell you my sinusoidal input is, let's say V in is equal to Vp sine omega naught t, where omega naught is less than P. So what will be the steady state error?
Constant.
Constant as in?
Because for omega less than P, the loop gain is constant.
Yeah, so it will be same as you get in case of DC. Because if I am talking about omega less than omega naught less than P, which means that I'm operating somewhere here. I'm operating in this region. My frequency of interest is somewhere in that region. In that region, my loop gain is constant. So whatever loop gain, whatever steady state error I was supposed to get at DC, I will still get at that frequency omega naught. Now note that this is Bode approximation, so it was never constant. But if we are willing to tolerate the error that comes through the Bode approximation, this should not be a problem. Okay, so in this class we'll be using Bode approximation through and through. So you should not bother about what happens at the edges. Okay, but if I now say that omega is equal to, let's say 2p, omega not equal to 2p, what do you think will be the steady state error? Or now, how will you approach? Yeah, but how will you approach? It will be high, but how will you approach?
Now loop gain is very less.
So can you, what is the loop gain at 2p? Or let me make it easier. Let me tell you this is 10p. Why? Firstly, in this plot, it never goes to 0. It's a log plot. So I hear somebody said a0 by 10. Is that correct or not? Incorrect? So what is the slope of this line? Yeah, so I mean, let's not bother about the +1 terms. So if so, what is the loop gain at 10p? 10p will be somewhere over here, right? I mean, let's assume that it's not up to scale. So I can always argue this is log scale. So if I have moved by a factor of 10 on the x-axis, how much have I moved down by on the y-axis? Pardon? 20 dB, right? 20 dB in terms of absolute means factor of 10, right? You don't seem sure, right? So you should be able to rattle these numbers out in sleep. So this should be a0 by 10. Right? So if you know that your loop gain is a0 over 10, right? So, and you know, then if you know the loop gain is a0 over 10, then you can simply plug in the value into the error formula, right? What is the error formula? Essentially this. I mean, this is not the error formula. This is V0 over Vi. So 1 minus this will be the error. And then you can figure out what is the final error. Now, one of you said that it's supposed to be 11 because it's 1 plus. But note that I haven't drawn the phase part as yet. Okay, so if there is a phase part to it, then this loop gain is not fully real. It can be, there can be a complex number associated with it also. Okay, so in that case, you cannot simply say 1 plus 10. It can be 1 plus some number whose magnitude is 10. Okay, so you'll have to be careful with that. So now, by the way, any questions? Yes.
What about the condition when E is greater than omega u by k?
Okay, we'll come to that. We'll come to that. Is an interesting case. So that is a part of this lecture itself. By the way, before I move on, if I say omega equal to 2p, omega not equal to 2p, what do you get? Here you said that loop gain is a0 is 10. So not a0, sorry, it's not a0 anymore. It's mod of L of j omega is 10. When omega not equal to 2p, what is mod of L of j omega naught? Sorry, this is a0 by 10, right? Thank you. So what is L of j omega naught in case of omega naught equal to 2p? So that is you have moved by factor of 2 on the x-axis. By what factor should you come down? In dB. In real? 2, right? So whatever, that's what log scale, log plot means. Whatever factor you go on the right, you same factor you go on the y-axis. So this will be a0 over 2. Right, from there you can go ahead and figure it out. Okay. So now let's sketch the phase part also. This is mod of L of j omega. And in case of an ideal integrator, you are getting this. So in case of an ideal integrator, what is the phase of the loop gain? How will it look like? 90, minus 90, right? So it will simply be minus pi by 2. Good. So now in case of a real integrator, how will it look like? Let me write out the loop gain expression for you. Yes. Yeah, so let's not bother about 1 decade and so let's get the intuition behind this. So what do you think? We're not bothered about when it will decrease, let's say, for at least for the time being. So how will it tentative plot look like? It will start from 0. Yeah, so if you just write out the expression here, so angle of L of S is minus tan inverse omega by P, omega by V. So naturally at omega equal to 0, it starts from 0. So around omega, at omega equal to P, it is minus pi by 4. And then it will settle at minus 90, minus pi by 2. Okay, so clearly if you have to take both phase and magnitude into account and say that my the ideal integrator actually behaves like a real integrator, or the real integrator actually behaves like an ideal integrator, then you will have to operate somewhere where the phase also has settled to minus 90 degrees, right? That's the that's the true mathematical way of dealing with it. But again, we'll ignore that part, at least for the purpose of this course. We'll not get into that. That level of detail. That is if you're interested, I would advise you to take the follow-up course 613. So we'll cover that there. Okay. So for the purpose of this course, as of now, let's ignore that, and we'll still go by this Bode approximation of the magnitude part, where we have everything in straight line segments, and we ignore the 1 plus term in the denominator. Okay. Okay. So if time comes, we'll look into how to take into phase from another perspective, but that is a topic for another class. Okay, fine. So now, so we also did this part that when L of S was an ideal integrator, right? When L of S had a DC gain, what was H of, what is the full transfer function? That is V0 over Vi. Closed loop transfer function for ideal integrator. Yes.
So when omega is much more than T, in that case, we have ideal characteristic.
Yeah.
So what type of ideal nature we are getting from the overall amplifier? Like in that case, the error should not be 0 because we are applying the AC signal.
Yeah, when I say ideal means what? It's an ideal integrator. And even an ideal integrator will not give you 0 error signal, right? Ideal integrator gives you 0 error only at DC, right? So yeah, so that's actually a good point, right? When we say ideal integrator, we covered it in the previous class also. An ideal integrator gives you ideal output, that is K times amplified output only at DC. Because ideal integrator behaves like an infinite gain block only at DC. Okay, so the exercise that we did here, figuring out what is the loop gain and figuring out what is the expected steady state error approximately, is also true for an ideal integrator, right? Even if let's say you have an ideal integrator and you are operating at omega naught equal to 10p, okay, what is the loop gain error? What is the steady state error that you will get? Is the same as you will get in a real integrator case, because you are operating somewhere here on this line after p, right? So if you're operating at omega greater than p, then it really doesn't matter whether you have an ideal or real integrator, isn't it? So you are not getting anything by making an ideal integrator if you are operating beyond the location of the pole. Because after P, there is no difference between what an ideal integrator would do and what a real integrator will do. Right? Okay, fine. I mean, maybe you would be interested if I tell you this is one of the very popular questions in placements. Okay, fine. So what is V naught over Vi for an ideal integrator? So let's do it in the form that we expect it, right? So what is the expected output? Expected output is K. Expected gain is K. And then if I express it in now in that form, no, in S domain, let's say this is in S domain. No, that is a loop gain. What is V naught over? Not the open loop gain. I have closed the loop. I want V naught over Vi. By S by omega U by K, right? Okay. So, so in this case, what is, we also did this, we superimposed V naught over Vi. By the way, the common terminology of V naught over Vi is H. Right? So let's use H. We'll not use the GH block for H anymore. So it becomes confusing otherwise. Let's use H for closed loop because that's what the literature does. So, so if I plot H mod of H for ideal integrator, so what will it look like? I'm only bothered about the magnitude response. We also did this. So what will it look like? So use Bode approximation. If you use Bode approximation, what is the breakpoint? Omega U over K. So before omega U over K, you will get flat line of K. And after that, yeah, so what will the slope look like? What will the expression look like, H of S expression? I can neglect 1 plus term, right? That's what Bode approximation means, right? I can neglect 1 plus term, which means it becomes, right? So omega U by S, right? So this becomes omega U by S. Okay. So now things become slightly interesting here, because if you look carefully, there are two things happening. One is something is happening at omega over K. Why is it breaking? Why is it constant till it almost behaves like an ideal scenario that we expect till omega over K? And what is omega over K? It's the point where you are hitting the 0 dB line. Okay. So that's why this omega over K is often called the unity gain bandwidth of the loop. Okay. So in this particular configuration, so in this particular configuration, omega U over K, we call it as unity gain bandwidth. Or in this case, we will call it omega U loop, because it's the unity gain bandwidth of the loop. Okay. So now, before again, one disclaimer before we proceed. This omega U, this unity gain bandwidth of the loop is omega U over K only for this particular configuration that we took, right? Resistor divider, factor of K with an integrator in the loop and so on. But you might not have this configuration. You might have some other, maybe a capacitor here, maybe a capacitor there, maybe another amplifier somewhere. So this expression of omega U over K will change. But whenever you plot loop gain, you will find a omega where your loop gain crosses 0 dB. Right? You will always find an omega where your loop gain crosses 0 dB, which is called the UGB of the loop. And that UGB, you will always find an omega u loop, essentially. You will always find omega u over k, or omega, you will always find UGB of the loop. And whatever be that UGB, we'll call it as omega u loop. In this particular test example, it happens to be omega u over k. Okay, so this is important because you will see that, I mean, this is a test case that we are running with. After some time, you will see that we'll replace this test case with a generic system where you can have multiple transistors. You might not even have a resistor divider. But if I plot the loop gain, you will get some frequency where the loop gain cuts the 0 dB line. And that becomes a very important set point for your analysis, right? Just like loop gain is extremely important while figuring out how your closed loop system will work. Similarly, omega u loop is a very important fundamental parameter of the loop that will tell you how the loop will behave. Okay, so whenever you get a loop gain, regardless of the fact that the question or the questioner has demanded you to plot it or not, do plot the loop gain. It gives you a lot of intuition. Okay. Okay, fine. So so this becomes your omega u loop or omega u over k in this particular case, and you see that something weird is happening. What I mean, the weirdity here is that before the loop gain crosses 0 dB, it seems as if, at least by the Bode approximation, things are perfectly fine. Right? We expected a gain of k, and we are getting a gain of k. And after that, something again interesting happens. It falls off, and it falls off. The loop gain falls off at the rate of omega u over s, which is the transfer function of the integrator. Okay, so there are two interesting things happening, and we would like to make sense of why this actually, I mean, maths checks out, but as a designer, we cannot be limited by what the maths is telling us. We'll have to also have an intuition behind why it's happening. Okay, so let's look into this. Look.
Loop gain also
So this is not the loop gain now, right? So this is the open loop transfer function that degrades at the rate of omega u over s. Okay, and this omega u over s degradation is consistent with the gain of the integrator if p equal to 0, right?
So H is the loop
closed loop gain. The closed loop, so the point that I'm trying to make here is that the closed loop gain seems to be following the integrator transfer function beyond omega over k. Okay. So now let's try to make sense of it. I'm going back to the ideal integrator case, because we know that at the back of our mind, if I put a real integrator, there will be a steady state error, and we'll take that into account when we are bothered about steady state error. Okay, if we are not bothered about steady state error, I don't want to do the extra algebra. I'll just get rid of the extra code. Okay. So now if I take you back to your negative feedback, classic negative feedback topology. So V naught is equal to 1 by approximately equal to 1 over beta when A beta is much greater than 1. And when A beta is much less than 1, what is V naught? A, right? So this is times Vi. A times Vi. So now let's try to figure out why, right? So what is this A beta much greater than 1 is saying? It's essentially saying that you have sufficient enough loop gain, right? If you have infinite loop gain, you get whatever you want. But in Bode approximation, what we are essentially saying is that infinite is basically greater than 1, right? We are doing straight line segments. So as long as things are greater than 1, feedback, there is some feedback which is coming back and correcting the error. It might not be able to correct it fully, but it's still doing some correction. Okay, so essentially before omega u over k, at omega less than omega u over k, I know that by definition, mod of L of s is greater than 1. Which means below omega u over k, or in this case, below omega u loop, in this case, which is omega u over k, your feedback works. So I can crudely say that below omega u over k, below the unity gain bandwidth of the loop, feedback works. Okay. And above omega u over k, when the loop gain falls below 1, feedback doesn't work. Okay. So here, feedback doesn't work. Or rather, simply say feedback breaks. Which means that the loop doesn't exist anymore. Nothing comes back to correct. Okay. So now see, it will make sense. When feedback works, I get whatever I'm supposed to get ideally. That's what the flat line segment means. Okay. That's what the Bode approximation also tells us. But when feedback doesn't work, what is happening? When feedback doesn't work, even though you have drawn a line and it seems that something is coming back, the strength of this error signal, strength of the whatever is coming back is very low. Right? Whatever we are getting back is inconsequential to correct the error, which means this, I can as well say that this line doesn't exist. If this doesn't exist, what is V naught over Vi? Omega u over S, right? So in this case, so for omega greater than omega u over k, V naught equal to omega u by S times Vi. Okay, and that's what you get. That's what you get here. Okay, any questions? So as you see that is quite natural to obsess over where the unity gain frequency of your open loop feedback system is. Okay, because if you are designing negative feedback to make sure that the closed loop system works as you want, which means that you would also like to know till what frequency your closed loop system will work properly. And that frequency happens to be the unity gain bandwidth of the loop. Okay, so that's why you will see that almost all amplifiers you pick commercially available, they will give you the UGB of the loop under some condition. Okay, because which essentially means that if you operate below the UGB of the loop, you will get the required output. If you operate above UGB of the loop, it will not work. Okay, so as a designer, that's why when you are designing for specification, if somebody tells you, hey, I want an amplifier which I have signals that to process which has 100 megahertz bandwidth. You have to amplify it by, let's say, a factor of 2. Okay, so which means you have to use a negative feedback, and the loop gain of that negative feedback loop should be higher. The bandwidth UGB of the negative feedback loop should be at least 100 megahertz. Right? Obviously, you don't want to get into a case where UGB is exactly 100 megahertz because this is again Bode approximation, and you don't want to be, cutting it very close. So you would want to leave some margin, but at least you know where to start. Okay. Yes.
So the conclusion is like the frequency beyond this omega u by k will have the ideal nature of the integrator, but due to very less feedback, due to less feedback, the output is the desired output is not exactly meeting what we desire.
Correct.
But at low frequency, although there is no ideal nature because the flat, right? But as the feedback strength is high, so our there is a feedback nature, negative feedback nature.
Right. Yeah. So that's what negative feedback nature. Negative feedback works if loop gain is more than 1. Negative feedback doesn't work if the loop gain is less than 1. Right. That's the crude way of distinguishing.
Good point is like T, where it has very
large gain. Yeah.
As well as one point that I'd like to see that Sir, that's for very low frequency, the phase is almost zero.
Yeah.
And around P, the phase is linear, right? So in that sense, also the P, the region around the P is good.
No, I mean, why would you say so? I mean, what is so holy about having linear phase?
Sir, actually, I knew like for the filter, the input output phase should be linear.
But that is for some particular application, right? Not necessarily for all applications.
So, sir, for amplifier, it is not.
It depends, right? I mean, okay, what does linear, we'll get to that. What does linear phase mean? Okay. Okay, so any questions?
Sir,
Yes.
I have one doubt on the feedback bubble of diagram.
Okay.
Not this one, because the response of this total negative feedback is low pass filter, right?
Okay.
K times.
Yeah.
So if we simply put on low pass filter, say RC filter.
Yeah, yeah.
Will it work?
What do you mean will it work? It's a low pass filter, yes.
Yes. So, but we have to do the low gain should be very, very high.
Yeah, right.
How can we
That's a good question. So his question is, where this expression, right? So this expression, if you ignore the value of K, is indistinguishable from a RC low pass filter, right? It's 1 by 1 plus something, right? Firstly, I mean, then what's working? What's happening? So firstly, if you use a first order RC low pass filter, you cannot get a gain of K, right? But if you want to use a unity gain feedback, right? If K equal to 1, then seems like it's an RC low pass filter, right? Okay, so what's happening? As it turns out, I mean, we can also show that you can model an RC low pass filter using negative feedback, but the intuition is as follows. I mean, I will not get into that now, but the intuition is the fact that if you hit this with a step, this voltage is going up, has gone up suddenly, right? The current that is flowing through, right? The current that is flowing through is high, or rather VI by R effectively, because this voltage hasn't changed, right? So the current is large at time t equal to 0. Then what is the steady state current? 0, right? So the system is trying to reach steady state. Okay, system is trying to reach steady state, and how is it trying to reach? The voltage on the capacitor is opposing the current that is trying to flow into it. So if you consider this to be the error to be the current, then it's basically the negative feedback is trying to oppose the current flow, right? So you can model this system as a negative feedback also. But obviously you don't get a gain out of this, right? Yeah. And there is another problem in this case. There's a loading effect in the sense that you are drawing current out of it, current from the source. Sometimes that might be acceptable, sometimes that might not be acceptable. Okay. Okay. So now let's hop back to our real integrator system, and we'll just use the same logic as we did just now. Okay. So in real negative feedback, the only thing that differs from the ideal is the fact that you have some DC gain. And everything kind of remains the same, right? If I ignore the phase for the time being, so it still cuts. It's still my omega u loop is omega u over K, and still my feedback works below omega u over K, and it doesn't work above omega u over K. And as a designer, what do you want your P to be? It should be very small with respect to omega u over K, comparable, very large. What do you want P to be? You would want the P, right? You would want the 3 dB bandwidth of your, open loop system to be as small as possible, right? Because note that in case of an ideal integrator, that P is essentially 0. Okay, which means the 3 dB bandwidth of an ideal integrator is 0, right? So if you are trying to hit an ideal integrator, if you are trying to mimic an ideal integrator, you would want to make the P to be as low as possible. Now, another thing to note here is the fact that This I missed, so let me go back. I'm sorry for this back and forth. So let me pull it down. Let me mark an important statement. And the important statement that I want to mark is that whatever we have seen till now is a first order system. Okay, so as it turns out, for a first order system, first order all pole system, because we see we don't have any zeros here. So for a first order all pole system, the UGB of the loop, that is omega u loop, is equal to the minus 3 dB bandwidth of closed loop system, right? So that's what it turns out to be, because it turns out from the maths, it checks out from the maths, but also it checks out from the intuitive argument, because your breakpoint of your closed loop system is omega u over k or omega u loop, because the feedback works below this and feedback doesn't work above this. Okay, so as you will see that, I mean, this statement is fundamentally true, that for a first order system, your UGB of your closed loop system translates to the 3 dB of your closed loop system. Now, this is fundamentally true for a first order all pole system. This is not fundamentally true for any higher order system. But the systems that we will be using in this class, firstly, it will not be first order, and it will also not be generic. So the systems that we'll be using in our class, you will see that we'll have a characteristics in which this statement becomes sort of true for most cases. We essentially means that we will postulate that for most systems that we are interested in, as long as you figure out what is omega u loop, then regardless of the order of the system, we'll postulate that the 3 dB of the closed loop system will translate to the UGB of the open loop system, or vice versa. Okay, the UGB of the open loop system will translate to the minus 3 dB bandwidth of the closed loop system, regardless of the order of the loop. This is what we'll postulate. Now, you should note that this is a rule of thumb, because this is not fundamentally true. Okay, so as a designer, our job will be to ensure that something like this stays valid. Okay, so which means that if you have a higher order system, we like to make sure that it kind of looks like a first order system when I am cutting the UGB, because if you are only looking around, if you are only looking at the loop gain plot around the UGB of the loop, that is, I keep magnifying it, it should look like a straight line, and the slope of the straight line should be minus 20 dB per decade, right? So we will I will again not prove this. So what we'll try to do is we'll try to ensure that the slope of your negative feedback loop gain looks like minus 20 dB per decade at a first order system when you are cutting the UGB of the loop. Okay, so that will ensure, that will kind of ensure to a first order that it looks like a first order system, which essentially means that my 3 dB bandwidth relation between minus 3 dB of the open loop closed loop system and UGB of the open loop system still holds true, right? Again, approximation, rule of thumb, but we will try to follow that. Okay, so if I, without again going into the proof of it, I leave the proof to you, do it yourself. Without going into the proof of it, what will be the closed loop approximate closed loop transfer function? How will it look like on a Bode plot if I have a real integrator, right? So this is my L real of S. Now what will be my H real of S look like? Use the same logic, intuitive logic. How will it look like?
It will have a gain of k up to omega u by k.
It will have a gain of k up to omega u over k.
Then minus 20 dB per decade.
And then it will drop off at minus 20 dB per decade. Correct. Right. So I would encourage you to do it yourself, validate that this indeed is mathematically true. But from the arguments that we laid out, it seems that it should work, because again, in this, since the UGB of the loop hasn't changed, I mean, mathematically, you will see there is an extra term because you have some extra term going on, but you will see that that extra term will be negligible with respect to omega over k. So we can neglect that extra term, and then which essentially means that my UGB of the loop hasn't been impacted, at least by the Bode approximation. If the UGB of the loop hasn't been impacted, if UGB of the open loop system hasn't been impacted, then the 3 dB bandwidth of the closed loop system should also not be impacted. Okay, so which essentially means that I need not necessarily fret about not having an ideal integrator. Right? If I cannot get an ideal integrator and I still want some bandwidth of the closed loop system, then I should be satisfied with whatever I am getting, as long as my bandwidth of the system is, the UGB of the system, open loop system is the bandwidth of the closed loop system. And I should not bother, because even if you have an ideal integrator, you will not get infinite gain at all frequencies. Okay, and obviously, I mean, even though we make a big deal about DC gain, you never achieve DC, right? To achieve DC, you have to wait for infinite time. So always you will have some error, as long as you are satisfied with whatever error you are getting. Okay, so so now let's look at the same thing with. Okay, so one of the important takeaways from this argument is, I mean, one of the important takeaways of how to ease your algebra is the fact that if you are not bothered about the steady state error, you can ignore P. Right? So it's important, so let me write it down also. If we are not concerned so this will ease your life, your algebra quite a bit. You don't have to carry around some pesky terms which are essentially not giving too much value. But obviously, if I ask you to figure out what is steady state error, then you cannot ignore P. It goes back to that condition that you cannot neglect anything with respect to 0, but you can neglect something with respect to large value. Okay. So now, if we are not bothered about steady state error, then we can assume it's an ideal integrator. And if it's an ideal integrator, if our input is VIT is equal to, let's say, VP sine omega naught t, what will be V naught t? So if I just give you this information, if I just ask you this, input is VP sine omega naught t, what is V naught t? What information do you need to give me a fairly accurate approximate answer? Yeah, you would like to know where the omega naught falls, right? Is it below, before, or after? So now let's assume it falls below, it's within the loop gain, right? So let's assume omega naught is less than omega u loop. So then what will be my output? K times Vp sine. Yeah, so now here is the problem. So we have, I mean, what I have essentially not showed you is how does the phase of the closed loop system look like? Okay, so what will the phase of this closed loop system look like? This is a first order system with a breakpoint at omega u over k. It will start from 0, right? Because you note that your transfer function is low pass type. So it's some k times 1 by 1 plus s by omega u loop, which means at DC, your closed loop phase is 0. And it will be minus pi by 4 at omega u by k. And it will settle to minus pi by 2 at t tends to infinity. Okay, so if that is the case, then which means that here you will have some term which is tan inverse omega by omega u loop. Okay, does that make sense? Okay, and when omega is much greater than omega u loop, and this is less. This is again approximate because I am neglecting steady state error. So when omega is much greater than omega u loop, what will V naught t be? Then negative feedback doesn't work. If negative feedback doesn't work, then what do you expect it to be? No, right? By k times b, the feedback doesn't work. Yeah, in this case, you don't have a. Right. So now omega u by s, that is in Laplace domain. In time domain, what does it mean? Yeah. So it's an ideal integrator, right? So you're integrating sine. So in other words, you will essentially get whatever input was there, right? So you will get the gain of the integrator, that is omega u, and you have integrated it, right? So which means omega naught will come out, right? Sine omega naught t minus pi by 2. Right, that minus pi by 2 comes because you have additional phase of pi by 2. Okay, so it's basically nothing but you take sine and integrate because it has gone through an integrator. It's a straight path. You don't get all these k terms because feedback is not working. Okay. So now one interesting thing to observe here is that, okay, by the way, I mean, again, these limits are important because one might tend to think that if omega naught is 0 and I'm using the second equation, I'm getting infinite V naught. That's not true because obviously, I mean, the equation on the second equation is valid well beyond omega u over k, where the loop gain itself is much low, which means that you're operating at omega naught, which is much greater than omega u over k, and definitely more than omega u. Okay, so now let's come to this expression of what is happening to V naught t when omega is less than omega u loop. So V naught t, I can express this again in this form. So if omega is much less than omega u loop, then tan inverse that term is essentially that term itself, right? Tan inverse x is approximately x. So this should have been omega naught. So I can express this as t minus 1 by omega u. Okay. So this is omega naught to be much less than omega u loop. So this almost looks like a case where the output is amplified by a factor of k, but also delayed by some time, right? So essentially, what is this looking like? This is looking like I cannot draw this. It's a system. The input is a sinusoid and the output is another sinusoid which is amplified, but it also has been delayed. And the delay is 1 by omega u. Okay, so we'll not get too deep into what happens if you have delay. I mean, this is if you have delay in the loop, this is not a delay in the loop per se, this is the end-to-end delay. But what I would like to point out is that, again, you see that, I mean, this omega u loop plays a very important role, especially at low frequencies, because essentially you can model this entire thing as a delay element also, right? So it's like a delay line. I wouldn't say delay line, but I mean it's a block which not only amplifies your signal, but also delays it. Now sometimes that delay might be wanted, sometimes the delay might not be wanted. It depends upon what you are trying to do. As the case he was pointing out, sometimes you want linear phase filter. So in case of linear phase filter, maybe you would want a delay, because a linear phase translates to constant delay, right? So in some applications you might want, but in some applications you might not want. So it depends on what is your specifications. Now again, if you don't want delay, which means you have to make sure that omega u loop to be as high as possible, right? So as long as you can make omega u loop to be as high as possible, it should be fine. Right? So again, it depends on the specifications for which you are designing. Now, another interesting, we'll not get into, obviously, I mean, we are out of time today, but we again will not get into this part. But since I have a minute, I'd like to make a point, is the fact that your negative feedback system So when we intuitively plotted the output with respect to the input, even before, I mean, this is going back to three or four classes back, when we intuitively plotted V naught over Vi over step response, what did we see? We essentially said that if Vi is a step, your V naught tends to increase, and this error voltage comes back, the feedback voltage comes back and reduces the error. If this is VE, the VE starts from a high value and it reduces, and it keeps on, this dog catching its tail kind of thing keeps on happening till everything settles to zero, right? V settles to zero. Now, I mean, sometimes what it may end up happening is that there is some delay in the loop, right? Not this delay that we just talked about, but there can be some extra delay. Okay, so maybe, I mean, I can model that delay as some extra delay in the loop. So, and that delay, the effect of that delay is essentially the fact that the feedback information comes after some time. So it may so happen that when the feedback comes, your output has already overshot. Right? It can happen, right? I mean, you must have seen while you might be riding your cycle or something. If your brake is bad, you drive slow because the feedback comes later, right? So essentially what might happen is that if you have delay in the loop, intuitively you can assume that there can be some case where the output can overshoot because because of the delay, the feedback, the error voltage is coming after some time. An extreme case of that is that if delay is infinite, then your output will keep on ramping. There is no feedback, right? But if the feedback eventually comes, then you might correct and you might undershoot, you might overshoot, and so on. These things can happen if you have delay in the loop. Now, again, the treatment of this is beyond the course, beyond the scope of this course. But what I would like to point here is that note that a pole in a system, right? If this integrator we model as an ideal integrator, but it's not necessary that, in fact, you will never get a single pole system. In reality, everything that you get has multiple poles. And if you have multiple poles, you might model it as, let's say, if you have a 2 pole, you will model it as something like this. So now this pole is, I mean, if I only consider on the concentrate on this 1 plus s by p2 term, this is similar to this. And this essentially translated to an ideal delay. Okay, so an additional pole can result in a delay in the loop. And if you have a delay in the loop, the feedback can come later. And in that case, you can have overshoots, undershoots, and in worst case, some extreme cases, you might have instability also. Okay, so this is something that I wanted you to leave with, because you shouldn't think that just because I have negative feedback, everything will track each other. Everything will track each other as long as your error information is coming on time. If the error information is not coming on time, then you have to take some corrective actions, right? So we'll see what corrective actions you need to take later on this course, but not from this ideal delay perspective. Those things is left for 613.
Sir,
yes.
This type of pole can give ideal delay or
within some frequency, right? As long as you can satisfy omega is much less than the pole, right? So then you can, the tan inverse, whatever, can be expressed as that argument. Then it becomes an ideal delay.
So like PD for the delay PD, it will be like minus PD in the Laplace domain.